Hi guys, my name is Samuel Jasper from CSE department. My topic for object-oriented software engineering is on software engineering for computational science, past, present, and the future. Let's get into introduction. Computational science is an interdisciplinary field that uses computers, mathematical models, simulations, and data analysis to solve complex scientific and engineering problems. Software engineering plays a critical role in computational science by ensuring that scientific software is correct and efficient. Yes, we live in a modern world where the technology is being evolved in a rapid and a very fast way. The technology that we use is very advanced and is done by mathematical calculations and simulations and also through data analysis on how the data is being used by the people, the audience, and the users that are in a broad world. And also managing the software and the computational science that is beyond the software is very crucial. We need to maintain it and we need to be very correct and very efficient, and we need to be very uh, very precise to scale it and maintain it and reproduce it to the next generation. Over time, software engineering practices in computational science has evolved significantly, moving from signal ad hoc programs to large collaborative high performance and intelligent system. Like I have said earlier, the we live in a very modern world and very tech evolving world where the tech is evolving very in a rapid fast way. It's very important to scale and maintain it. We have gone to a very advanced level where we went from writing ad hoc programs to now writing an artificial intelligence program and high performance program and low level designs and many more. Past, how let's look into how the past computers were and how the past computational science is all about. Characteristics. Software was written mainly by scientists and researchers. Back then, we didn't used to have software engineers like we do today, but many programs were written by scientists, scholars, researchers, and many more. Programs were monolithic, poorly documented, hard to reuse or maintain. They were very hard to debug and very hard to maintain it, scale it. If we want to scale it to, we need to rewrite the whole program that is written by the researchers or PhDs and many more. Let's look what are the technologies that they have used to write such programs in the past. They used to write only C, Photon, very basic programs back then. These two programs were widely used back then. And also one popular model back then was batch processing system. This system is like, you bring a bunch of programs, you put it into the system. What the system does is slowly executes one after one process. So it takes one process, it completes the whole program, and not only that, it takes a very lot of time to execute such a small program and a tiny program, and the output is not guaranteed in such a way that you will always get the output. No, it's not that way. It's very 50-50% chances. Most of the time, they used to get errors on the program that they have written. No version control, no GitHub, nothing. They just used to write in papers. They sometimes used to save, and that that was not an it's not very updated, not far tech such way. What are the developments that they have done in that way? No formal software methodologies, no solid principle, no design principle, no operating systems, no computational networks, no architecture on how to handle the systems, nothing like that. Manual debugging. They used to manually debug. They used to write a bunch of big programs, and they used to debug every single line they have written. They need to go through the workflow, dry run every single thing. The limitations, difficult to reproduce it. These write big programs, no guarantee that they will get results. High chance of hidden bugs. Sometimes what they used to do is they used to write very big programs. Debugging was they were adapted to debugging. They debug, but the debug was not in the program that they have written, but in the system that they are running on it. So such are the limitations. It's very hectic and very not precise, to be honest. This is what all the past computational science software is all about. Let's look into the present software that we are living in. Characteristics that we have currently are, it is very software engineering is now recognized as an essential and very demanding and very high paying skill that is currently on it. It emphasizes on reproducibility, reliability, scalability, maintenance, and debugging, and many more technologies that we have, right? Python, C++, C, C hashtag, .NET, Java, Julia. Julia is no the most popular language that is being evolving right now. And the libraries that we have: NumPy, Skitlearn, TensorFlow, SkyPy, Pandas, and many more. These technologies are used in high-performing computation, HPCs, cloud computing, GPS, and parallel programming. These are the technologies that we have currently, and softwares that we use are version controls, GitHub, uh, and they are the more. We also save it in like file structures sometimes in VS Code, Jupyter Notebook, and many more. It's many modular and layered architecture, automated testing and validation. And also we have continuous integration where we debug the whole program that we have written, or not by us but also the other person, software engineers. For example, the core documentation and core reviews are done in a way it is very precise, transparent, and easy to understand the code that they have written. This is what we currently have. Let's look into what future brings on. Future next generation of computational science software. Emerging trends. The trend that we have currently is on artificial intelligence, machine learning. Very artificial driven software engineering is wholly focused on automation, intelligence debugging, and AI assistant simulation design, where we get an artificial intelligence or a computer to assist us to to make us move forward and make our task easy and very computational and transparent and accurate. And extremes, large scale and computational systems like massive scaling small system to large scale system with the help so that no interruptions occur in between the user and the server, and they get in contact with the help of the scalability tool, reproducibility and sustainability, fair principle, example solid, many more. Challenges: managing roles of the complex. It's very hard to scale the small system into large system and multi-component systems. Code bases can span hundreds of thousands of lines, so it's very hard to debug. Dependencies between modules become difficult to manage. Limited software. We have very limited software, may lack in training, software architecture, design patterns, version control, testing methodologies, and very hard to extend, reuse, or debug over time. Reproducibility of scientific results. We have differences in hardware platforms, challenges and changes in operating systems and libraries, missing documentation of software versions and parameters, non-deterministic behavior in parallel and floating point computation, and performance and maintenance control. You know, mm, by running these programs on a system, we need to have very large GPU and very high performance computers. So getting them, it's very high cost and very inefficient. It can get go around out of budget too. Scalability across computational platforms. For example, multi-core CPUs, GPUs, distributed clusters, cloud environments, and etc. Solution: applying formal software methodologies like solid principle, ad hoc manner, implementation, testing, and maintenance. We need to write our code in a modular way, layered way, reusable architectural way, so that it simplifies debugging and etc. Software conclusion. Software engineering solutions play a crucial role in addressing the challenges faced by computational science by adopting structured development methodologies, modular and reusable architecture. Practices such as version control, automated testing, thorough documentation, and reproducible research techniques significantly enhance the correctness, transparency, and creditability. Thank you. Hi.